Hello everyone, this is Mr. Lee. We are starting the official new chapters of calculus today. We'll do section 1.1 and 1.2. I will say that the homework is primarily over 1.2. 1.1 is primarily about introducing you to what calculus can let you do. It's mostly a section you can read, but I put some important information down here. Everything you've done before this course is technically all under the umbrella of pre-calculus. Every algebra class you've taken, even any trig or pre-calculus classes you've taken, they've all been under that umbrella. The difference between calculus and all the things that come before it is that calculus deals with a lot of dynamic things that are happening and changing inside your functions. So things like finding the limit as something approaches a value instead of just evaluating a function at that value. Previously, the only thing you could find the slope of was the slope of a line because it had constant slope over the whole thing. But using calculus very quickly, you'll be able to find things like slopes of curves, velocity given position, the curvature, tangent planes, the direction of motion along a curve, area underneath the curve, things like that. We may not get to all of them in this course, but between calculus 1, 2, and 3, you do hit all of these things. So below here is just a list of the different things that you will be able to do when you are done with the entire calculus sequence. Now, that said, we'll look on the next page. It's great to know all of the things you can do, but we shouldn't really get ahead of ourselves. We've got to get there and learn how to do them. In order to get to calculus, there's kind of an intermediate step between taking what you've already learned in algebra and trig and developing the main ideas of calculus, which are derivatives and integrals, and that little bridge section between the two is called limits. Now the limits kind of help you identify what is happening on certain graphs, and we'll look more into that as we keep going. The only two things really 1.1 does to define that I think are important is to define two concepts, the tangent line and the secant line. So the tangent line of a function at a point represents a line that has the same slope as the function at that point and also passes through that point. If you look at this picture on the right, you have this curve, y equals f of x, and at point P, we have the tangent line. Now notice the tangent line kind of runs right up next to the function and keeps going. It's a line that kind of approximates how the function is behaving at that x value. Because previously, the only thing you could find the slope of were actual lines because they had constant slope. But tangent lines help you find slopes of curves at smooth points on the curves at any point on a function. Now, how does a tangent line compare to a secant line? A secant line, it takes 2 points on a function, finds the slope between them, and uses that to approximate slopes between the 2 points in question. Now, you'll notice that the formula that the book has used, which I've listed here, is it's f of c plus delta x minus f of c over c plus delta x minus c, which simplifies to the right. But you may know this much more similarly to the difference quotient, how we did f of x plus h minus f of x over h. Notice that these are very similar, only the notation is slightly different. I do not care which notation you use. I will always be referring to it in the same way that we referred to the difference quotient. One interesting thing about the secant line is as that second point on the secant line gets closer and closer to the first one on the graph, you get closer and closer to the tangent line approximation at the point. Here's an example of how close we are getting to the tangent line as the point on the curve Q moves closer to P. Now, since we've just done the difference quotient in our algebra review, you should be somewhat familiar with how it works. And that's about all we're going to touch on from 1.1, because 1.2 is really where the math begins. So 1.2 is all about limits. As an introduction, it's kind of helpful to walk through a process here. The limit kind of represents what's happening as you get very, very, very close to that x value. We do not care what's happening actually at that x value. We just care it appears to be happening as we get close to it from the left side and the right side. For example, on the right, we have the graph of the rational function f of x equals x cubed minus 1 over x minus 1. If you factored this, it would cancel out the x minus 1's, and you would be left with a regular quadratic. So you'll notice that that means when you remove a fractional expression, portions of it, from the function itself, it creates a hole in the graph, which you should have seen in rational functions in the past, in algebra, and possibly even in pre-cal when you went over it. Now what results is the hole, the indeterminate form. So the way we handled this in the past is we would say x cannot be 1, and we would just draw a hole at where it would be in the rest of the equation. Limits don't actually care what's happening at that point, so the limit is going to check what y value do we appear to be approaching as we come towards 1 from the left and we come towards 1 from the right. If they're meeting at the same value, we can say that the limit is whatever that value is. It does not matter what's actually happening at that x value, it just matters what's happening when we get very, very close. So the concept behind a limit is that we can have potential locations where values are not defined, but still have a grasp of how the function is behaving as we get close to that point. So looking at the picture, it looks like as our x values get very, very close to 1, our y values are getting very close to 3. So we can say that the limit as x approaches 1 of f of x is equal to 3. Alternatively, from doing a graph, is you can use a table of values and plug in x values that are getting closer and closer to 1. Here's an example of what the table would look like. We don't know what the function's value is at 1. In this case above, it's undefined, but we can plug things really close to 1, like 1.001. As you see, as we get closer and closer, we're pinching towards 1 from both sides, and you can see the y values. Look, at first, when we were about a quarter away from 1, it wasn't super clear. One's 3.8, the other's 2.3, but as we got closer and closer, we got y values that are converging, kind of approaching the same point from both sides, and that further reinforces the idea that the limit as x approaches 1 of the function is 3. Now the way we will write this is we will write lim to represent limit, and then underneath the limit we will write x and then an arrow to represent x is approaching some x value, and then we'll have the f of x, and then it's equal to whatever the limit is. So this says the limit as x approaches 1 of f of x is equal to 3, or you could say the limit as x approaches 1 is 3, because we're going to already know the function in question. Starting in the next video, what we're going to do is actually do some examples of this using a table, and then possibly use a graph to confirm the behaviors.